Okay, so my first weekly test was not done particularly well, particularly with the mechanism. And I know what the problem is, well, what I perceive is that it has been a long time since you guys have been dealing with mechanisms. And I can see that are some fundamental problems with this. We need you to get to a stage where you find the mechanisms intuitive and that they make sense to you. It's not going to help for you to learn mechanisms in such a way that you're learning something in a parrot fashion. It has to be something which comes from understanding the flow of electrons and how they move forward. So you may need to go back to some earlier chapters in your textbook just to cover that material again to get that right. I really do encourage you to come to grips with this, these sorts of things, mechanisms, because they're going to be important for you later on, and we do want you to do well. If you get to understand them, I can guarantee you that all the rest of the chemistry is going to flow very easily, and you know, with everything that we're doing. Okay, so in this case over here, a lot of people got confused by the ethanol over there. That's just a solvent in this reaction. It doesn't take place, it isn't involved in the reaction really, and it's OH is not a leaving group. It's not an electrophile. This molecule. It's just a solvent, and for all intents and purposes, you can ignore the fact that it is there. In all mechanisms, one of the key sort of points to remember is that if there's an acid present, the mechanism should not end up with minus charges, and if there's a base present, you should also not end up with things that have protonated, in other words protons, H pluses floating around. Okay, so what happens here is that the proton activates the carbonyl. Let's not forget, of course, that the proton can also protonate the nitrogen. Just in terms of the mechanism, nothing much is going to happen. So we don't draw that out, but it is something that can occur. So on protonation of the carbonyl, we're actually activated. And in activating it now, the amine, right, from the pyrrolidine, is able to attack there, right, and these are all actually equilibrium. We can now form an OH over there and an amine.
And if you go back to first year, you will recall that this over here, oops, mustn't forget the H. This is actually aminal, a aminal. And what can happen now is that a proton transfer occurs, and proton transfer occurs where this proton will leave and another proton comes onto this oxygen over there. So that H is picked up, lone pair of electrons, and this H can disappear. So overall it's a proton transfer PT that's occurred, and now we've effectively changed the OH into a leaving group, and the nitrogen has its lone pairs free again so that it can do the next step, which is to kick in and kick out the leaving group, which is water. Again, this is an equilibrium, and we're now left with the, now some people stopped at this point and they called this an imine. It's not an imine because the nitrogen is positively charged. It's an iminium. Okay, you didn't have to write this down, but I'll write it here. Iminium, intermediate. And now at this point, drat, I've lost space over there. The two H's that are there, right, can now be picked up by something. We could have used the ethanol, we can use the water that was given off, but they pick up the H and the electrons are donated in like that to form the amine, like so. That's the amine. which would have been the answer to this question. Okay, so that's the mechanism that's occurring over there. It's a lot of arrow pushing, but there is a rationale behind what's going on with that. Okay, and you must come to grips with that. Please practice these sorts of mechanisms. I'm going to be asking more. I really want to make sure that you understand this. It's one of the reasons we do these tests, by the way, is so that you can come to grips with this work, and we know where the problems are later on. All right, so this question over here said, give a couple of reasons why this reaction won't work. A lot of you said that sodium hydroxide is too weak a base to deprotonate over there, and that's why the reaction won't work. I didn't give you any marks for that. It is a true statement, but there's actually a more glaringly obvious problem to using sodium hydroxide than it being too weak a base. The analogy is kind of like you're walking along in the veldt and you come across a lion, and you're then asked to describe what the problem is. And one person will say, well, the lion is going to eat you, which is the obvious and big problem. But another person will say, well, the lion is going to give you fleas, which is going to cause you to scratch all over. Well, that might also be true, but it's not really the big glaring problem. And the big glaring problem with using sodium hydroxide with an ester is that the sodium hydroxide is going to hydrolyze the ester, and we're going to end up with the carboxylate, the carboxylic acid, once we protonate it. All right, plus methanol. So that's what sodium hydroxide would do to that. And then the next problem with this reaction, and almost all of you got this correct, is of course that this is a tertiary bromide, and tertiary bromides or alkyl halides do not undergo SN2 reaction, so therefore no SN2 reaction. So that's is why this would not work, because if you did form the enolate there, you would need to, it wouldn't react with that. We would have to use a silyl enol ether to get something like this to work. Notice just in the question, not many of you did, but there were numbers who gave solutions to this problem. Just be careful when you look at questions, see what the question is actually asking. Here it's saying, for the following planet, give at least 2 reasons why it will not work. It's not asking for you to give a way that this will work. All right, so be careful when answering questions, just to give what is needed. All right.